Hello, we are Space Team Aachen from Germany. With 200 active members, we are the largest technical student initiative in Aachen, with members from two different technical universities, RWTH Aachen and FH Aachen.
Our initiative works on multiple space-related projects involving rockets, satellites, or scientific experiments. Since last year, we've been working on Scorpius, Space Team Aachen's first Mars Rover project, to extend our expertise to the field of planetary exploration.
Our Scorpius team currently consists of 14 active members, which are structured as follows. Sarah and Max are the project leads of Scorpius. They manage and coordinate the sub-teams and the project budget. Additionally, they handle the communication with the board, the other projects and Space Team marketing. The work on the rover and drone is divided into 4 sub-teams: software, mechanical, electronics and drone. The software team is led by Niklas. He is responsible for handling the gamepad inputs, video stream and hardware communication. The other members are Nihal, who works on the data collection and system monitoring, and Jeremy, who works on the physical computations and configuration management. Sarah assists with the software structure and programming. Joachim leads the mechanical team. He constructs the rover's body, locomotion system and end effector. The other members are Eike, who works on the manipulator, as well as Manuela and Alejandro, who work on the drill and simulations like FEM for both the rover and the drone. Furthermore, Max also helps with rover manufacturing. The electronics team is led by Christian, who works on the stepper driver board and the hardware interfaces. The other members are Toby, who works on the power distribution system, and Cem, working on the power supply. Gabriel is responsible for sensor feedback of the motors, and Reynold focuses on firmware development. Another Niklas leads the drone team. He designs and programs the companion drone Panopide. Manuela helps with the manufacturing of the drone. We see the European Rover Challenge as a great opportunity for students to share their curiosity about space exploration. We are eager to apply the interdisciplinary knowledge gained by our studies to Scorpius and continuously improve our rover to be more capable.
Since Scorpius is our first rover and we expect many changes, we've opted for a modular design. That's why we're using standard 2020 and 2040 aluminium profiles. Even though this isn't the most elegant or lightweight solution, these profiles are easy to reuse and allow us to quickly change dimensions and iterate on the design. For the suspension, we decided to go with the rocker boogie setup. There are 2 main reasons for this. First, it offers excellent off-road capability because all wheels are always in contact with the ground. And second, it allows us to use 6 wheels instead of 4. That way we can use affordable direct drive hoverboard motors instead of more expensive geared motors. The tires are 3D printed from TPU and use carbon fiber reinforced nylon 6 rims. Thanks to their internal structure, they provide some dampening while still maintaining a large contact patch on the ground. The differential bar is mounted on top of the rover to prevent collisions with obstacles and to maximize ground clearance. The front and rear wheels can rotate more than 90 degrees in both directions, which allows the rover to turn in place. For steering, we are using NEMA 17 stepper motors with 50:1 planetary gearboxes and magnetic rotary encoders. Right now, many locomotion parts are still 3D printed prototypes. These are gradually being replaced with aluminium parts. However, based on our tests, some parts are reliable enough to stay 3D printed and be reprinted in carbon fiber reinforced nylon 12. The body is enclosed with aluminium panels to protect the electronics from water and dirt. Inside, the rover is split into 3 sections. The front features headlights, a depth camera and a 2K camera. These are protected from rain and direct sunlight. The battery is located in the center section within the chassis axis of rotation. As the battery is the heaviest single component, this minimizes the load on the differential. The battery case is 3D printed from flame retardant material and the cells are dampened internally to absorb shocks. All the electronics are mounted in the rear section, where it is cooled by 2 fans. Air is pulled in through the protected front intake, flows over the battery and the electronics, and exits through a water-resistant duct on top. On the top there are 2 additional systems. A signal light with 3 circular rows of addressable LEDs to indicate the rover status, and a camera turret with a 2K wide-angle camera. A telephoto camera and a flashlight are also planned. The turret can rotate freely horizontally and about 180 degrees vertically. The 5 degrees of freedom manipulator will be mounted to the front, and the drill, including the sampling containers, will be mounted on the rear. Both systems are still in development and will be built soon.
Our electronic system is made up of a combination of commercial and self-designed components. For example, this stepper driver board is an in-house design, where together with the software team we defined a communication protocol which can flexibly address this PCB via USB, Ethernet or CAN bus. Our battery pack is made up of 16 lithium phosphate batteries in an 8S2P configuration, having a total capacity of 40 amp hours. We chose lithium phosphate batteries compared to other battery technologies for their improved safety while accepting the slightly lower energy density of the cells. Our power distribution system includes an emergency relay which cuts off power to all motors in case the emergency stop button is pressed. To reactivate this relay, one has to manually press a button on the rover, ensuring that no software can override our emergency stop system.
As a new team, we decided to make our software flexible and modular. Therefore, we based our system around Docker containers and web technologies for communication between them. With this approach, we are able to use whatever suits our needs best for each subsystem. On the main node of our operating system, we use an object-oriented Python program to abstract all the rover's hardware components and handle communication with the PCBs. Additionally, the UI is part of the main node. We use a web-based UI framework which can be accessed by multiple devices at the same time. This allows us, for example, to control the rover with this Steam Deck and simultaneously visualize telemetry data on a laptop. Another node handles the database, for which we use QuestDB as it is quite efficient at storing time series data. For the video streams of all the cameras, we use GStreamer in a zero latency configuration and MediaMTX as a distributor, such that internal systems for example, computer vision and the UI clients can access the streams simultaneously.
Regarding the drawing subtask, we use a self-built frame. It's called Panopedea and consists out of a self-milled frame which has a base plate, and underneath we mount the arms with the underplate. The underplate also has a quick release system for the autonomous system, and therefore we can quickly exchange the autonomous system or also get rid of it and fly the drone in FPV mode. This way we can also tune the PID controllers and so on without having the autonomous system mounted. For the propulsion system, we use 10-inch props with 3215 900 kV motors, which allows us a high maneuverability even with the heavy load of the autonomous system mounted. All of the drone parts are milled with a CNC mill, and the carbon fiber is also laid out by ourselves. We use prepack for this and made the arms out of 7mm carbon fiber, and the base plate and underplate and so on are made out of 3mm carbon fiber plates. For the software, we use PX4 in off-board control mode. This allows us to control the drone within Raspberry Pi, where we run a ROS2 program, which controls all the maneuverability that we have. Therefore, we can use image detection and computer vision to quickly find the probes that we are supposed to detect in the task, and also land safely on the Aruco marker that is given for the landing spot. As a data link, we use ExpressRS to not only have the data of the drone itself, but also have the telemetry data to a ground station. This way we can not only control the drone, but also the autonomous system with the same telemetry link, and don't need external devices for this. On a ground station, like any normal laptop, we can just view all the details